The goal for us in ARS is to produce data for technologies that will improve the safety and wholesomeness and quality of food.
Meet Dr. Brendan Niemira. His food job involves seeking innovative methods to enhance the safety of fruits and vegetables. He leads a team studying special treatments using cold plasma and heat that can kill harmful germs without affecting the quality or taste of the food. Dr. Niemira is a lead scientist at the USDA's Agricultural Research Service, and he has published over 180 peer-reviewed research articles, book chapters, and critical reviews. He's clearly an expert in the topic of plasma, so I said to him, let's talk about it.
Sure, I'm happy to. Let me lead in, right?
So today you'll be learning about what Brendan does as a lead scientist.
I'm the administrative head of the project. There's 4 of us on this team, 3 scientists and 1 engineer.
Why plasma could be a game changer for food safety.
Well, if you keep adding energy to it, you start to break down the bonds actually within those atoms and molecules.
And how you can grow your career using food organizations. Thank you to the Canadian Food Innovation Network for sponsoring this podcast episode. Thank you so much, Brendan, for coming on the show. You are doing some really cool research, and since I knew that we were going to be having this call, I've been doing a lot of research into the cold plasma, what's it all about, but I mean, you're going to be able to talk about it so much better than me talk about it. So thanks so much for coming on the show.
Sure, I'm happy to be here.
Well, to get us started, I know we're going to talk about cold plasma, but I want to talk about you first, just to set the groundwork. So maybe you'd be able to introduce yourself and what you do.
I'm Brendan Niemira. I'm a lead scientist for the USDA's Agricultural Research Service, and I work at the Eastern Regional Research Center in Wyndmoor, Pennsylvania, which is just outside of Philadelphia.
Okay.
I've been working for the USDA for coming up on 25 years, almost all of that working on non-thermal food processing technologies.
Wow. So how did you started off in biology, if I'm not mistaken, and then you're in this like very physics heavy chemistry realm. So do you mind if we could talk a little bit how you progressed to that area?
Sure. Well, actually, in a funny kind of a way, working with cold plasma and all the physics and plasma physics associated with that is a little bit like coming home for me, because I started off life as a physics major. I did my undergraduate work at the University of Chicago, and I started as a physics major. And then, I changed my major, as many people do, and I eventually settled and changed it to biology, because I got really fascinated with plants and plant physiology and plant microbial ecology. And in fact, I'm not a food scientist by training. I did my PhD at Michigan State University in the Department of Botany and Plant Pathology. So I'm actually a plant pathologist and plant physiologist by professional expertise. So it's, so how did I end up working in food microbiology as a food researcher? Well, so a lot of what I did in working in the plant pathology arena was to evaluate how plant pathogenic bacteria would grow on fruits and vegetables in storage, and to come up with ways to limit their ability to grow and to kill them. So it wasn't that much of a stretch when I finished my PhD and I, was working on this as a postdoc, to then I was looking for a job. Well, it wasn't that, big of a leap to look at, okay, I've already been limiting how bacteria grow on fruits and vegetables. So I would switch from plant pathogenic bacteria like Erwinia and Pseudomonas to human pathogenic bacteria like E. coli and Salmonella. So I was hired by the USDA, and I started working here in 1999, actually to work on food irradiation. Radiation treatment is a non-thermal processing tool to limit the growth of E. coli, Salmonella, Listeria, and other organisms on fruits and vegetables. And so that's kind of the path coming here. So then when the opportunity came up in the course of my research to broaden from just irradiation to encompass a few other non-thermal processing technologies, including cold plasma and pulsed light and high intensity light and monochromatic light, this really gave me a chance to use my physics skills along with all the kind of phytoplankton microbial ecology skills. So it was really nice the way everything kind of came together.
I love that. It reminds me of there's that joke where it's like a biologist says that it's just chemistry and a chemist says, well, or a physicist says, well, chemistry is just physics on a bigger level. So it's that deepening level. So you have to look at science as a whole. So it's really cool that you're able to kind of come full circle and bring everything together.
Yeah. Well, I mean, the way that it started was that we actually had some conversations. The team here had some conversations with some plasma physicists who were working on plasma applications and in non-food applications for material science treatment and for materials processing. And they thought that there might be, is there a possibility to work on it with food? Well, the food microbiologists and the food technologists that we had on the staff didn't really understand what these plasma physicists were talking about. They just couldn't get the same language. And the plasma physicists and engineers, electrical engineers, just didn't get it. They couldn't really understand what the microbiologists were saying. Well, when I came onto that conversation, I mean, I had a foot in both worlds. And so I was able to say, hey, guys, there's a lot of potential here. This could really be something cool. And they said, well, since you're the only one of us who understands it, why don't you take this ball and run with it? And so I did.
Look at that. Look at that. So currently your work is as a lead researcher, am I correct?
I'm a lead scientist is the title.
Oh, okay.
I'm actually a research microbiologist. And as I said, I work on technologies to improve the safety of fresh cut fruits and vegetables, but also low moisture foods like powders and ingredients and flowable foods like spices. But my role as a lead scientist is kind of an administrative role. So I'm the administrative head of the project. There's 4 of us on this team, 3 scientists and 1 engineer, and 1 support scientist. As a lead scientist, well, I write the reports and I keep track of the budget, right? I mean, that's because somebody's got to, right?
Yeah.
And so I kind of make sure that everybody is on track with that and make sure that when we're spending things that, the money is being spent properly and that we have all the tools that we need to carry our work forward without running out of money by the end of the year. So.
Pretty important.
Yeah. Yeah.
I find it interesting that, to be honest, I never really thought much about there being research being done at the government level because we think of a lot of the cutting edge research happening at academic institutions, industry, but I thought that the government was just for regulations and checking up on people, making sure that everything's okay. But I guess that's not the case.
Well, yeah, I am one of those government scientists you sometimes hear about. Actually, the Agricultural Research Service is the in-house research arm of the USDA. And yeah, when you think of the USDA, sometimes you think, oh yeah, they're the people that inspect meat, right?
Yeah, yeah.
Exactly. Well, those are my colleagues over in the Food Safety and Inspection Service. Or they're the ones that are at the border making sure you're not bringing in some kind of crazy pathogen. Well, those are my colleagues over in the Animal Plant Health Inspection Service, right? And they have a very, very important regulatory role. But the role of ARS, the Agricultural Research Service, is to perform research to address the critical problems and to pursue those very, very interesting, promising opportunities that are facing American agriculture, right? So that's kind of the way that we are structured is to pursue kind of longer term, high risk, high reward research in a way that maybe academic research or industrial research is not really set up to do.
That makes sense. And I think the key word is that long term, because a lot of projects at like the academic level might be 4 years, like funding's gone. Of course, I know you are at the hands of funding, but at least there's this longer term maybe thing that can really explore these issues.
Right. There can be that longer term investment in the project. And if you're working on something which is on a 1 or a 2-year grant, then you're limited by the terms of that grant, right?
Mm-hmm.
And so in an academic environment, perhaps if the funding cycle is 2 years or 3 years, then that's the time frame that you're going to be looking on. All of our research projects here at the ARS are funded on 5-year cycles. And so we, make a case for what we're going to do, the science that we're going to get, and the results that we expect to obtain. And more importantly, who's going to care about it? I mean, what's the value of this research that we do? Who is going to find it useful? Who's going to find it valuable for producers or for, our sister regulatory agencies? When we look out across the landscape of American agriculture and everybody who is producing all of the food and the feed and the fiber and the fuel, right? Those are the 4 Fs. When we do this research, my own particular research within ARS is related to food safety. We're developing food processing technologies. But we have people that are developing new test kits to detect new and emerging pathogens. We have people that are doing water quality stuff so they can know how pathogens move in the environment, human nutrition issues, developing new strains of plants or controlling new diseases that might be affecting animals or crops out in the world. So ARS does a lot of different kinds of research, all of which is designed to benefit producers and consumers of American agricultural products.
That's really cool. And I guess that's where the cold plasma comes in and how that's been, because I had never, honestly, prior to, our meeting, I know what plasma is, like I've heard of it, I know about it, but application of food, never even crossed that even existed. So Let's talk about it. Why don't you?
Sure, I'm happy to. Let me
you
lean in, right?
okay, I'll let you take it away.
So, well, I mean, first of all, why do this? Okay, I mean, that's the big question. Why are you working on cold plasma? It's because there's a need for advanced processing technologies that will kill human pathogens on foods or prevent them from attaching in the first place or prevent them from growing out to the levels that they can do people harm, right? Now, there are a lot of technologies that are already currently in use. You can heat food, or you can boil it, you can pickle it, you can brine it. There are certain sanitizing compounds that you can put onto these foods. But some foods are not very amenable to the kinds of aggressive treatments that are necessary to ensure that safety, right? I mean, if you take lettuce and you boil it, well, you certainly will have killed any E. coli that might be on it, but that's not very attractive. Okay, you haven't preserved the quality and the taste and the functionality. One of the things that we find with fresh and fresh cut fruits and vegetables is that many of the antimicrobial technologies that are available, sanitizers and gas phase antimicrobials and so on, they'll take the pathogen risk down somewhat, but they can't get it all the way down to the point that you don't have outbreaks associated with those foods. Now, the folks in this industry, I mean, are doing as a great job. I mean, they're really, really, really working hard. They invest a lot of time and money to do a really, really good job, but they do need these new technologies. And so there are a variety of them that are being researched by myself and by my colleagues in ARS and by people all across the country. But cold plasma is one that I started to work on because it's got a lot of attractive features, right? So you mentioned plasma. We kind of know what plasma is. So that there's three states of matter that everybody is familiar with. There's solids, liquids, and gases. And plasma is the fourth state of matter. And sometimes that kind of throws people off. Well, what exactly does that mean, and how does it relate to the other three? Well, solids are atoms and molecules that are kind of locked together. They're kind of lower energy. Well, if you add energy to a solid, then it kind of breaks down the bonds between those atoms and molecules, and they start to slide around. And now you've got a liquid. Well, if you keep adding energy to that liquid, now you've broken down the bonds between those atoms and molecules, and they start to fly freely floating individual atoms and molecules, and you've got a gas. Well, if you keep adding energy to it, you start to break down the bonds actually within those atoms and molecules. And now you've got free floating electrons, or you break apart an O2 oxygen atom into a singlet monoatomic oxygen. And all this stuff is really, really reactive. Okay. And so it's very, very effective at killing any bacteria or virus or parasite or fungus that it comes in contact with. So just from air and electricity, you've created this incredibly powerful sanitizing tool. And when it's floating around, these structures can then recombine with each other. So you take O2 and you break it apart into monatomic oxygen. Boy, that's going to really, really attack the organisms. But then that O can combine with an O2 to make O3. Well, now you've got ozone, which is another sanitizer. If you take water and put some water vapor into the mix, then the H2O will break apart into H and O. And so now that hydrogen atom by itself is just a naked proton. And so you get this acid effect. So you've got kind of an acidosis type treatment. That H and O can recombine with two of its other H's and O's to make H2O2. Well, now you've got hydrogen peroxide vapor. So starting with just air and water and electricity, now you've got a whole slew of complicated sanitizing molecules that go a long way towards eliminating all of the pathogens that might be present on foods. And when they are done reacting, they will react with each other and they'll just go back to being air and water. Okay, so there's no residues, there's no chlorine that you need to use, there's no organic acids that are involved, there's no ammonium ions that you're buying in concentrated form and applying as a chemical sanitizer. So there's a lot of reasons to like this technology. It can be very, very clean, very green, very efficient. It's effective against a broad swath of pathogens and target organisms, and you can use it on a lot of different kinds of foods. Anything from apples and lettuce and tomatoes, kind of high moisture stuff, but you can also use it on low moisture foods, spices, peppercorns. I've seen studies where they applied it to the surface of bread products to eliminate mold. You can apply it to grain to eliminate fungi that might lead to aflatoxin production. So that's some of the things that people are working on in this technology to move it forward and to apply it in the different ways that the technology suggested it could be used.
One thing that came to mind as you were speaking is, how does the plasma kill the organism but not affect the quality of the product?
So it's like any other technology. If you leave it running too long, then eventually it will start to degrade
Okay.
the product itself, right? So it's kind of a balance between when the stuff comes in. If the bacteria is sitting out there, it gets hit first, and you get membrane disruption, and then it'll die or it'll get injured. If you with the brief treatments that we're trying to apply, the surfaces of the lettuce or the cantaloupe or the tomato is not affected by the plasma because it's not strong enough to go through the outer tissue layers of the foods. One of the things that we've seen with when we're treating bacteria, like do a really short treatment with the plasma and then measure what kind of kill we get. You get a little bit of kill, but what's important is you get injury. You get sublethal injury that then makes those bacteria more susceptible to some other treatment that you apply in combination with the plasma. So an example of this, I did a study with my colleague DK Akuku, where we applied a niacin-based sanitizer to eliminate listeria on apples, and put it on there at a certain concentration, and left it on for 60 minutes and got a 3.5 log reduction, which is great. It's terrific. Terrific reduction. Well, if you treat that with, I think it was like a 30-second blast of plasma, real quick treatment of plasma, and then applied the niacin, you still got 3.5 log reduction. But instead of taking 60 minutes, now it only takes 3 minutes because the bacteria has been so weakened by the plasma that it just falls over and dies when you expose it to the sanitizer. We had the same kind of result when we combined plasma with high intensity broad spectrum light. Okay, that's with my colleague Siddharthan Mukhopadhyay, where we were applying the plasma. First we did plasma, then high intensity light, and then we switched it around. We did high intensity light and plasma, and it doesn't matter the order. With these things working together, provide this kind of synergistic interaction that gives you much better kill than either one would by themselves.
With this research that you're doing, how do you see it being implemented? Like if it was great and it worked for you, and then you wanted to have it implemented in the processing facility, like how do you actually see that tangibly looking? Is it, let's say if we're using, I'm thinking nuts, for example, would it be something that the nuts go through the conveyor line and they just go through like a wall of plasma? Is it?
Kind of, yeah. I mean, so
Okay.
imagine it like a car wash. Okay, I mean, so this is where it gets to be kind of a fun engineering.
Yeah.
And if I could, I don't know if you could, I will just stop my video. I don't know if can you see that image?
I can, yes.
Okay, so this is a test that we did, with a postdoc who was working with me, Dr. Sarah Hertrick, where we applied plasma to the surface of an orange and applied it. You can't see it in the static image, but the orange is rotating because we wanted to kill the salmonella that was on the surface of it and that was down in the stem scars and in the blossom ends. Okay. And what we found is that the plasma, because it's acting like a gas, it can get down in deep into those things where the chemical sanitizers are not really able to reach. So you can imagine that if you want to treat this, you want to apply this on a conveyor belt type system. Well, they're rolling down the system. You got the plasma jets up above, and they're hitting it like a car wash. You could also have different forms of plasma, like a dielectric barrier. That was a plasma jet that I was showing you. You can also have a dielectric barrier system where the plasma is creating kind of a loose field, and then it's almost like they're floating down a fluidized bed where you can blow the plasma up underneath, and so they're tumbling through the plasma going forward. We've done work where we actually generate the plasma inside a package that's already been sealed. Okay. Where we put lettuce inside a bag, inside the stuff, and then seal that up, put it inside a plasma field, and then turned it on and generated plasma inside the bag, and we were able to eliminate the listeria that was inside. Right. So this is after it's been packaged. That was with my colleague from Korea, Dr. Si-Chol Min. So it's fun because you can kind of, once you start to think about how you can apply this, there's a lot of opportunities, and it gets to be kind of exciting. It's just like kind of limited by your imagination. You can imagine in a bagging facility, lettuce goes into the bag and the bag is sealed up. And then before it goes onto the truck, it takes a little detour and it goes under the plasma machine. The plasma is generated in the bag as like a bacteriostatic or bactericidal treatment, and then it goes onto the truck. And then the truck goes off to the wholesaler. And as it comes off the wholesaler, before it goes into the cooler, hey, it might take another little detour and get treated again as another little bactericidal, bacteriostatic treatment. Even to the point of it's out there in the store or it's at point of sale, point of service, it could get another quick little treatment with plasma as a final little, sanitizing process. And you don't have to worry about washing off, if you use sodium hypochlorite or quaternary ammonia, you would have to wash some of that stuff off. You don't have to do that with plasma because it's not generating any new stuff that's not going to be there originally. It's just the air and the electricity working together to make these sanitizing molecules that then recombine with each other and go back to being air.
For the listeners that are listening, I'll make sure to link the video in the show notes so those that want to see the video of the plasma can, so that'll make it easier. But when I just find it so, it seems as though it has the potential to be inserted in many different regions. Like it's not like a large scale, like I'm thinking giant fryers or something where you have to have like a big setup. It sounds like a plasma does have the capabilities potentially being very small, portable. Am I understanding that correctly?
That's a really, really good point. A lot of times, if you want to sanitize, let's say a conveyor belt, right? During processing, you need to have a tank of some kind of concentrated sanitizer, or you need to have something that's spraying onto it. You have brushes and rollers, and this is a large, heavy thing, right? It does its job, but you can't very well put that on the back of a truck and drive it out into the field very well. Okay, you can, but it's kind of cumbersome. If you have a small portable device that all it needs is air and electricity, and of course the electrodes that you're using to create this, it's entirely feasible to say, well, look, I'm going to mount this onto a tractor, and I'm going to use the generator. I'm going to use the power from the tractor's motor to drive the PTO, the power takeoff, to drive the generator that's going to fire the electrodes, and then just pulling air, an air pump. You're going to filter, of course, you don't get bugs and twigs into it. But then you just put that across the electrodes and you spray that right in the field. You could theoretically use that to treat the plants themselves, which I've actually seen. I mean, I've seen pictures of industrial scale equipment. It's still in the R&D phase. It's not, quite yet ready for prime time. But this R&D phase where they're actually spraying plasma onto plants as a sanitizing process. Or, if you're familiar with how a lot of, vegetables are harvested, out, California, Arizona, wherever, you would have a crew working on a truck or working on a flatbed that is being pulled by the tractor. And things are being loaded onto the conveyor belt. They're doing trimming and packing right on the site. Well, if you want to have some kind of a process where you could keep the knives clean, or you could keep the conveyor belt clean, or you could theoretically keep the workers' hands clean, you don't want to necessarily have to be hauling around 100 gallons of sanitizer that's then going to have to be dumped someplace. If you just need air and electricity, then these could be mounted on these mobile units, and then they could be positioned wherever you want them to be. Okay, remotely sited in the field, so they could be spot treating where the problem occurs, maybe before that bacterial contamination problem comes back to hydrocooling, or to sorting, or to shipping, or to the packing shed.
I like that as well, that it sounds that it adheres to, in school, we've been taught about the 12 principles of green chemistry, and one of them is reduction of chemicals, try to keep workers safe in that. So it does sound that this technology has the potential to help with these types of things. But one of the things that stood out to me was, so you've been involved with this technology for a long time, and you've seen as it's grown, but working at like a government level, at what point did you figure out this is an actual viable solution? Like this is safe enough to be put out into the public? Because that is one thing I think about with new technologies. It's like, how do you figure out there's enough information that we can deem this safe? Like, is it just that there's enough tests that have been performed? What has shown you that?
There are a couple of critical points along a technology development scale, and this is not the conventional technology readiness scale that you might be familiar with for commercialization. I'm just talking about, like, if you see something, you think it'll be cool, you think it'll be a good idea, and you think it's worth investing your time and energy as a scientist in developing this. There are a couple of key points. The first point is where you know enough about the technology to say, hey, this is going to be worth me investing some time and energy into it. And so you do. And then if you get some good results, you don't even, at that stage of the game, just the initial proof of concept, you don't even really necessarily need great results. You just need results that are good enough that they will support your belief that this is a big enough hook that you can hang a hat on and that you can go forward with that. The next phase is convincing your boss to let you work on it. Right? And you might get enough data, so I'm convinced, but now that's not good enough. You have to be able to convince the people that you are responsible to. And that's, you work in government, you work in academia, you work in industry. You're going to have to go to somebody who is, setting the work schedule and who's paying for all the research and say, hey, I think this is a valuable thing for us to be working on. And you're not going to convince them just with, charm and enthusiasm. You have to have the data. I mean, that helps, but you need to have the data, you need to have the technology, and you need to have a timeline for how long you think it's going to take to get this to the next level, right? And we were fortunate in that we started to work on the plasma that as soon as we started to work on this to reduce, I think it was listeria that we were first trying to initially reduce. We saw some reductions. We saw enough reductions that I was able to carry this, up the chain and say, hey, I think we should spend some time and money on this. And they said, well, you can let me spend time. We'll let you spend a little bit of money, but we don't have enough money to allocate to this because it wasn't originally part of the budget. So we kind of had to get sort of creative, right? And we put together some things sort of from first principles. And instead of buying the fancy equipment off the shelf, we went and we bought cheap equipment where we built it ourselves out of bits and pieces we got from the junkyard or from garage sales and stuff like that. But all of this stuff was based on the scientific principles behind high voltage electricity and plasma physics and food microbiology. And we were able to put this stuff together, and then we started to get some really nice results. We were able to say, hey, this is really something special. Okay. At a certain point, however, again, on this, this kind of technology development point, there will come a point when somebody, it might be one level above you, it might be two levels above you, who are going to come and say, I have no idea what you're doing. This plasma sounds weird. I've never heard of this. Why are you spending your time on this? And you need to be able to respond to that with solid data, with a technology development plan. And you need to be able to say, look, these are the prospects. This is the potential that this technology holds. This is why it's a good idea for us to write this into next year's budget. Okay, so that we can really develop this and go forward. At each stage of that, I mean, I was fortunate that, the people that I was working for and the people that I was working with, we're able to be sort of scientifically open-minded and say, yeah, okay, I can see where this, where this could work. I can see where this could be something that we want to go with. So we will give you the freedom to work on this and give you the resources to carry this to the next step. And then once that happened, then you go to the next step. You build it a little bit bigger and you build it a little bit bigger and it kind of snowballs forward. And now, 20 something years later, you see with kind of being relentless in talking about this and explaining it to people and saying what the potentials of it are, you start to see other people get on the bandwidth and they can see, oh, hey, I see potential in this other direction. And that's great. Just take the ball and run with it in 100 different directions. And that's where the whole technology, you get cross-pollination, you get people talking to each other, you get a lot of different ideas and a lot of different technology that moves everything forward on a lot of different fronts.
So it doesn't matter if you're in academia, it doesn't matter if you're in the work world, it doesn't matter in government, you have to have a plan and you got to convince somebody to do something.
You've got to have a plan and you've got to have enough data. I would say it's a pretty rare person who can just go in with the charm and enthusiasm and make things happen. If you don't have some solid data behind it, charm and enthusiasm will only carry you so far. In the world of science, eventually you do have to produce data.
Yeah, I think science is built on data and getting it's kind of our stick, so we need to be able to do that.
Right.
With this technology, is it commercially available at this point, or like if let's say someone is so like, I think this is great, I'd like to start implementing this in my factory or something, I really see the potential, like, is there a commercial option that they could even implement it currently, or are we still in that phase of talking about it?
There are companies that can provide you with plasma machines. Some of the stuff is used in other industries, like it's used in the paper industry or it's used in the textile industry. In those environments, like if you treat paper with plasma, it changes the surface energy of the cellulose fibers of the paper to make ink stick better. So you get vibrant colors using less ink. It'll make dye stick to textiles better. So you get better, adhesion of textiles. In the food industry, there's still some adaptation of some of those existing technologies to make it work precisely on what you want to do with food.
Yes.
Mostly because food is complicated, right? I mean, even if you say, well, you've got one plant that does almonds, another plant that does pecans. You say, hey, they're both nuts. How different could they be? They're very different. And the way that they're applied to those two different kinds of nuts, you really need to adapt the technology so that it's suitable for that commodity. I mean, I said that the plasma is at a really interesting point. I think when I first started out, the big question was, does this work? And over the course of years, I think, I and a lot of other people kind of answered that question and say, yeah, it does work. It works pretty well in a lot of environments. So now the question is not, does it work, but will it work on my commodity? Will it work on my product? And then the bigger question, can I use it and make money doing it? Can I solve the problems that I'm trying to solve? Can I create those opportunities and pursue those opportunities that I might want to pursue using this technology? And that's where you would start to see real implementation in a commercial environment. The big, one thing that is happening right now is that people are looking at this, are doing pilot scale testing. They're doing this kind of large scale testing in the field and in manufacturing facilities. The USDA's FDA and FSIS also, they haven't yet issued rules on exactly how plasma would be used in a food processing environment. Okay, so if you're a food manufacturer, you say, "Hey, I love this technology. It looks great. We want to do it. We want to pursue this." The current rules are not set up to allow that as of yet. So what's going to have to happen is somebody's going to have to go to the FDA or whatever other controlling regulatory authority, if it's in another country or something, and say, hey, I've got this technology, this plasma that I want to use for this particular purpose on this particular food commodity. Is that okay? And then show them the data that it works and show that it works reliably and so on. And then they'll have that regulatory conversation. I work for the Agricultural Research Service, and so I'm not a regulator. And so I don't have an awful lot of insights into how my colleagues over the FDA would make their decision, what their decision-making process is, and what kind of information they would need. But I know that people do this all the time. I mean, when they wanted to use high pressure to treat food, or they wanted to use microwave-assisted thermal processing, or they wanted to use other kind of chlorine dioxide, they went to the FDA and said, hey, I've got this technology and I want to use it. And there was a back and forth. There was questions about how are you going to use it, what are the context, what product, how intense are you going to use it, and so on. And then eventually the FDA issued a ruling. Yes, you can use it this way. You can use it on these commodities, but not on those commodities. You can use it at this concentration, but not on that concentration. And that's the regulatory framework in which all these other technologies are working. And cold plasma
I
will
love
just follow
asking
the
that
same
question
path.
because it's always a conversation that I have with others when I go to these academic conferences and I'm listening to about this research or how something's really cool. And then I look at the industry side and I'm like, where's that jump? Because sometimes it can be, it feels like two different worlds where they want the same outcome, but getting that translation, getting it into the factory or getting it actually implemented, it's I think in its own piece in the puzzle, I just think is a fascinating area, even though I love the science.
Right, right. And in a laboratory, you could have a technology that is so cool and is so awesome, so fantastic, works really, really well. But if it's too complicated or it's too expensive or it damages the food or it creates some kind of a toxic byproduct, well, that's not going to be used commercially, right? I mean, these are insurmountable hurdles. The goal for us in ARS is to produce data for technologies that will improve the safety and wholesomeness and quality of food in the food safety arena in a way that preserves all of the necessary attributes that a food processor, a wholesaler, or distributor would need to have in order to make that food available to the public, right? So the public wants to have safe food. Producers want to produce safe food. And we want to provide technologies that facilitate that. I mean, that's the whole, we're all working towards the same goal, but you need to keep in mind that there are various priorities that people have all along this production and sales chain.
I don't know if you can speak to it currently, but you've established that you're working in this field, but what are you currently like exploring now that you've established, okay, cold plasma works with foods, like, so currently, are you looking to improve the efficiency of it? Are you looking to improve the different range of products that it works for? Is there anything that you're specifically kind of have your eye on that you're aiming for with your research?
Sure. Well, there are a couple things that I'm working on that are still so new. I'm just still not sure they're going to work, so I don't want to talk about those. But one thing
Okay.
that I'm working on is plasma activated water as a way to use plasma injection into water to replace or to supplement chlorine-based sanitizers in wash tanks. So when you harvest lettuce in the field or tomatoes or oranges or whatever, they come in on the truck and then they go into a tank. And there's usually, or I should say very often, there's two stages of washing. The first stage goes into a water and it removes the bugs and the twigs. Then there's another stage that will give them really a proper wash. And this wash tank will often have, it frees all the small particulates and things on it. That's an area where you can have cross-contamination. So if you have one head of lettuce or you have one apple or one, watermelon or something that has some kind of a pathogen on it, when it goes into the water, those bacteria or parasites or whatever can then float around and they can contaminate everything else that's in that tank. So now one bad apple becomes 1,000 bad apples. To prevent that, these wash tanks will often have sodium hypochlorite or calcium hypochlorite or other kinds of chemical antimicrobials injected into the water. At the concentrations that are used commercially, they're not really super effective at eliminating the contamination on an individual piece of produce, but they're quite good at preventing cross-contamination. So with the plasma, you can envision a situation where instead of having the chemical monitors on there and every few minutes it injects a little bit more sodium hypochlorite, which can lead to chloramines being produced and some other kinds of chemical residues. Instead of that, if you've got a continuous injection of this cold plasma, then that may be replacing that or supplementing the chlorine so that you don't have to use so much chemicals. You don't have to use so much quaternary ammonia or chlorine dioxide or sodium hypochlorite in the wash tank. And then if you use this, then there's no residues and then that can come out. So that's one of the things that we're working on. I mentioned earlier about some of the combination treatments that we're doing, combining plasma with high intensity light and with chemical sanitizers. That work is ongoing so that we're trying to get really short treatments of one and really light treat. So a short treatment of plasma and a light treatment of the antimicrobial sanitizer to get a really, really good kill, better than you could using either one really hard on its own.
Wow, that sounds really, wow. I like the idea of shorter times. Like, I think that's a really big key
Right.
for producers because, cleaning things and soaking and all that, it takes a lot of time because it's more efficient the longer you are. And I know that you did mention about the plasma times, but like 30 seconds that's like nothing.
And well, if you've been in one of these facilities, you see the things move
Yes.
fast. All right.
Yeah.
They moved on the sorting line, and you often don't have a lot of time. I mean, sometimes in sitting in your lab, you might think, well, I only treated it for 2 minutes. Hey, on an assembly line or on a sorting line, 2 minutes is way too long. So some of the treatments that we've tested, like we did stuff looking at how plasma could inactivate biofilms on food contact surfaces, and we deliberately limited ourselves to treatment times of 5 seconds, 10
Wow.
seconds, 15 seconds to say, well, look, if this is all the time that you have, how much kill can you get? And in fact, even on biofilms, which are notoriously very, very hard to remove, even those short treatment times with plasma, we were able to get multi-log reductions of E. coli and salmonella, or E. coli and salmonella biofilms in just 15-second treatment. So you can imagine that if you're doing end of shift cleaning or you're doing continuous cleaning or conveyor belts, if you have the plasma there and you get that short exposure to plasma, you can really, really reduce your risk of cross-contamination from biofilm associated pathogens, right? And this is something that chemical scrubbers take higher concentrations and a lot more effort to do. Okay, so this is one of the areas that's pretty fascinating to be working on.
I could see the potential even in the grocery store. That's where cross-contamination can happen at food service or at the grocery level, just packing, cutting up fruits even with safe handling practices, there is always a risk of something happening at the grocery level if someone's just repackaging. So that'd be really cool as maybe like a future aside.
Sure. And if you're talking about this technology, again, that doesn't use any chemical sanitizers and doesn't leave any residues behind and is completely dry, Well, there's a lot of opportunity to put that into a lot of different places along the food handling chain, including right up to the point of service in a food service environment.
And is this a high energy? Because we're talking about ionization, or we're talking about this process that sounds like it's very energy intensive. Is it?
It's high voltage, but it's not
Okay.
necessarily high energy. Okay, it
Okay.
doesn't necessarily consume a lot. Like the system that I just showed with the orange, that uses about 500 watts, which is
Okay.
which is about maybe a third as much as a toaster might use. Okay, if you use a hair dryer at home, that's maybe 3,000 watts. My hair is short enough, and I don't need a hair dryer. But if you use a hair dryer that might be 2,500 or 3,000 watts, so you could run 6 of these plasma units for what it would cost you to run one hair dryer.
Wow.
Okay,
Okay.
that's the energy intensity of your production. The big key is to get the voltage high enough. And this is sometimes, people get a little bit caught up on the amps versus the volts. The voltage is the potential between the electrodes. And if you crank that up high enough, that barrier from the electricity jumping from one to the other, if the voltage goes up high enough, that's where the air molecules start to be torn apart, and that's where you generate the useful things in the plasma.
Mm. Oh, wow. Wonderful. I would love to keep talking, but I do want to just get a little bit more on the side about just you because I have you on the line and I just wanted to talk about
Sure.
you've been really involved in IFT and all that. I know that's something that our listeners would also be interested to learn. And I know that you've been involved in leadership development. And one of the things that I wanted to just ask is that for many students that are looking to grow their careers throughout in the food industry and such, have you seen anything that you find that they're maybe missing, or maybe that there's something that you notice that, hey, maybe if more young individuals had this skill, they might push forward more in the industry, I guess.
Uh, this is an interesting question. It's an interesting question
Okay.
because I know that a lot of people, a lot of food scientists participate in IFT and
Yeah.
IFP, IAFP, and ACS and ASM, whatever. And they go to the conferences and they attend the meetings and they present their results and they don't ever have any desire to be involved in the leadership stuff. And that's fine. They get a lot out of the meetings with the networking and the fellowship and connections and collaborations and stuff. But if you are interested in doing some of that leadership stuff or developing those leadership skills, right? If you think that you just want to do that for yourself, or you think that it'll make you more valuable for your current employer, or maybe pursuing a new job for a future employer, or you just want to provide that as a service to the service to society. I think the big thing to remember is that it all kind of starts with people, and it starts with networking, and it starts with relationships. When I was first starting out as a scientist, going into some of these things, I didn't know anybody, right? And it was kind of intimidating to go to these meetings and to see
Yes.
some of these leading lights, right? And man, they knew everybody. Everybody knew them, and it's, oh my God, it's so hard to even think, what it would be like with them. I think the biggest thing to realize, you shouldn't let that stop you. Okay, I mean, yeah. So this is a whole different kind of a quanta of stuff, but just get involved with the things that you want to do. Find those divisions or professional development groups or whatever it is, and just start getting involved. Attend the meetings. Volunteer to review paper submissions for the annual meetings. Be a judge at poster competitions. Get involved to do all this stuff and make those connections, right? And as you connect with people, so the other people who are also going to be poster judges, they will be higher than you, okay? And you'll be in the right room, right? You'll be rubbing elbows with some of those other people. You will get to know them, and as you connect with them and as you start to do some of these things, that will open up opportunities for you. All right, I've seen this happen. It always happens. Once you are in the room and you start to know some of these people, then it starts to get better. Then once you have some of those experiences, people know who you are as they are sitting around in some of those big rooms, the room where it happens, where they are starting to think, who would be good for this? Who could we tap for this? And, I just met this person, and I think that she would be really good for this task force, or she would be really good for this committee. Okay, and then that way you can kind of get connected to that. Maybe be bold. I mean, sometimes people are not as confident about being bold for volunteering for things as they might otherwise be. Put yourself forward. I volunteered to work in IFT. I volunteered to work to review papers for I was in the non-thermal processing division submission. I did that for years. Met a lot of people, and it was really, really terrific. And that led to volunteering to work on the annual meeting scientific program committee. Okay. And then that led to me chairing AMSPAP. And then that led to me being on, running for and being elected to the board of directors for IFT. And then my experience there, I'm on the leadership development committee for IFT. I think every time you do this, you start to meet some of the right people and you start to make some of those right connections, and you demonstrate to them the skills and the abilities that you can bring to the table. And if you do that right, and you can show that you being in the room is an asset to that committee, to that task force, to that organization, that people are going to want to have you in that room. And that's where things start to move along for you.
And is this or with the poster judging or reading the papers, is this open to, this would be for young professionals, correct? Like that are out, or is it also students?
It's open for young professionals.
Okay.
I think each society has different, sort of rules about, whether it would be students. I don't think that you would see a situation where you'd have some students judging other students' work, but for young professionals, you certainly would. In IFT, there is the IFT Student Association. IAFP has a comparable organization, ASM, ACS. There's always these, these organizations and these teams within for students to get to know each other. And, you're all students together. Well, in 3 years or 5 years, or hopefully not 7 years, but at some point, you're all going to be young professionals together, right? And you're all still going to know each other, and you're all still going to be able to kind of connect in that kind of cohort. So make those connections, reach out to people, volunteer your time, and you get back what you give in. That's what I like to say, right? I mean, and if you invest in your network has the opportunity to bring you along and invest in you.
I like that. For you, what has been some of the things that you have gotten out of your network as you've done all these amazing things being involved, but has it been maybe ideas for your research? Has it just been connecting to the right people? That might be a personal question, but
no, I think it's a great question. I have absolutely gotten ideas for the research. When I go to the meetings and I sit in on a session that has either nothing to do or it's only tangentially related to my research, it gives me a different perspective on some of the things that I might be able to do for mine. But I absolutely have found collaborators. I found people to write grants with, people to pursue funding projects with, service on other kinds of committees. That each one of these then part of if you're interested in doing this kind of leadership development, or you're interested in just doing professional development for yourself, part of that is to let people know what you can do and what you're available to do and what you're interested in doing. If you're not interested in reviewing or judging posters, hey, maybe you might be interested in being a grant reviewer. If that's not your particular cup of cocoa, maybe you would be interested in doing developing the program for an annual meeting, the scientific program, right? Or submitting symposia at your favorite annual meeting. That's a way to get connected with people, to reach out with people, to invite them to be part of this process and to move all of this stuff along. So yeah, I mean, I aside from the great friends that I've made
of course,
doing all this network, it makes the meeting a lot more fun when you know
That's true.
people and you can walk across the meeting floor and you can shake hands and you can just kind of connect with all these great folks who are like you working on food. When you're talking to people who don't work on food, sometimes it can be a bit of a slog. You kind of have to explain what you're doing. These people get it. They are your tribe, and they're right in line with you and your passions, right? So you can all kind of be passionate together. And that's really a great feeling, right?
I like that, being passionate with one another. That's a really good one. And I also think that when you're reading these grants, you're reading all these different aspects, you get to, figure out what works for you, or maybe just like, oh, I never thought that might be a good way to articulate my thoughts in that way in the future.
Right.
If I'm ever applying for a grant, of course, not copying and pasting it, but seeing like the way someone, like what's an effective one, and then maybe you might see one that's not as effective and you're like, oh, I might be a little closer to that. So there's also that benefit even from the outside peers.
And when you're in the room with some of these people, you can ask some of those awkward questions you're sometimes afraid to ask, to say, hey, how do I apply for that grant? I mean, I just read that you just got this grant. How did you get that grant?
Hmm.
How did you write it? And who did you work with? And they will be, people by and large are very friendly, and they will be happy to explain to you, what they did and how they did it, so that you can then learn from them, and then you can carry this stuff forward, and make it work for yourself and for your colleagues, and and then 10, 20 years from now, you'll be able to turn around and do the same thing for an up and coming young scientist who's got a technology that she wants to develop, and you say, look, what this person needs is a little bit of confidence, a little bit of support, and a little bit of a helping hand. You could turn around and then bring along the next generation of food scientists.
I can just imagine what the energy was like. I think you were just recently at the Food Safety Summit.
Yeah.
It must have been amazing, the energy in that room.
Well, as it happens, if you want to see my presentation of the Food
Oh,
Safety Summit,
okay.
the talk, this is kind of funny, but my talk, it actually is still available online at the Food Safety Summit. They recorded it, and it's still available for a year. It was new era, old problems, emerging pathogens, and dealing with emerging pathogens. I'm the third speaker of three, so the whole session was great. But if you just want to watch me, you can fast forward to the end.
Okay, a great segue for that one. Yeah, no, that's cool. I love, since I've grown for myself, starting as a master's student, getting more involved with conferences and feeling like I've seen a little bit of progress for myself and getting involved. It's been really nice to just be able to talk to people more, feel a little more confident, not be so stuck in I'm just a student. Like I've never, like I think everyone gets that, but you start to make friends over time, and it's nice to be work colleagues, but then as well just talk about other stuff. And that's a really nice thing as you grow your career, that I'm really enjoying that aspect.
Yeah, it is really good. I mean, the colleagues and the friends, it's great to see. I mean, some folks, I might see them online here or there, but when you go to the meeting, that's where you see them in person, and that's where you can, go off and have some hors d'oeuvres together, and really, reconnect with those stuff. That's really what makes it makes that people think of networking. Oh, this is so hard. It's a burdensome.
Yeah.
Well, it can be a little bit challenging, a little bit daunting, but the rewards are so tangible that you really should invest the time and energy to do that.
Mhm. It does get a little bit easier, especially when you know one person and it's not like this very stiff, oh, I want to talk to you. Sometimes it's just, hey, I know this. You're in a circle talking with one person that you're friends with, and then they talk to another person. Then all of a sudden, here's another conversation. It wasn't you actively networking to get out there. It
Right,
was just a conversation.
right, right. Yeah.
Well, looking at the time, we are already at the end, and it went by really fast. And I'm looking, honestly, I'm going to be looking more into some of the other talks that you have, where you do like a full hour on the cold plasma, which is on YouTube, because I think that it's a really interesting conversation. And I'm really happy we're able to share this with the audience, because it was new technology for me, and maybe it might spark an interest for someone to go into that research. So
Yeah. Well,
thank
it's been a joy for me to be on Food Grides with you, Veronica. I really appreciate the invitation to come join you.
Before I let my guests go, I just wanted to ask two more questions. We'll make it quick.
Okay.
What advice would you give to students that are looking to go into food safety?
Food safety is a great field to go into. I would say if you're looking for this, decide what you want to do. Do you want to study the bugs? Do you want to study the environment? Do you want to study the technology? Do you want to study whatever the context is that you want to do on that? Understand what are the big problems? What are the big unsolved problems in that environment? If you're trying to develop a new technology, you're trying to understand the behavior of some organism, you're trying to understand, some kind of environmental issue, how they survive or thrive in an environment, how they become contaminated. Understand what the big problems are, because the easy problems are either solved years ago or they're of no interest to anybody. Find out what the big problems are and see if you can make a contribution on those. That's where you're really going to change the world. That's where you're really going to make food safer for the greatest number of people.
Like that. And then the last question is, if people had questions for you, where could people find you?
Well, I will be at IFT. All right. So if you're
Okay.
at IFT, I'm giving one talk on science communication on
Ooh.
IFT, there. I think I've got one poster, two, I think at least one poster that I'll be doing. So I'll be around the hall. So if you see me, come up and say hi. I'm happy to talk to you. Online, you can find me on LinkedIn. If you just do a Google search on my last name, Niemira, and USDA, then that'll bring up all those
Okay.
that stuff that you mentioned. Or you just email me directly, brendan.niemira@usda.gov.
Amazing. Well, I'll leave it at that. Thank you so
Right.
much for coming on the show, Brendan, and sharing your information on cold plasma. I love it. And this was a great conversation.
Sure, you bet. Thanks so much for having me.
Wow, that was a really cool conversation. And who would have thought that you can apply plasma to the field of food safety? I'm looking forward to seeing how this field of research is going to develop and how it can eventually be implemented into the food processing industry. Once again, thank you to the Canadian Food Innovation Network for sponsoring this podcast. And if you enjoyed this science-based episode and you want to learn more about other cool food tech, then check out my conversation with Dr. Sripat Jose, who is the operations manager at Arda Inc. They are doing some really